Welcome to the deep dive. We're doing what we do best here. Sifting through a bunch of information this time, it's all about understanding two variable data and pulling out the golden nugget so you can get a handle on it fast.
Right.
Consider this your shortcut to being data savvy.
Exactly. We've got a really interesting collection of materials lined up, covering pretty much everything from the basic building blocks of, data display to the smarts behind designing surveys, spotting when things might be skewing your results,
Twice, yeah.
different ways to collect data, how to see the connections in that data, and some key statistical tools to make sense of it all.
Our goal for this deep dive is, well, simple but powerful. To give you a solid grip on how data gets collected, how it's organized, and maybe most importantly, how to actually understand what it's telling you.
Yeah, the interpretation part.
We want you to be able to see the stories within the numbers without feeling like, your brain's about to explode. Okay, let's unpack this. We're starting at the ground level. Two variable data sets.
Right. So a variable, it's just something we can measure or count, like someone's height or the number of cars on a road. Pretty straightforward.
Okay.
Now, a categorical variable is a bit different. Instead of numbers, it deals with categories, things like different types of fruit or the days of the week.
Got it. Categories, not numbers.
Exactly. And a dot plot. Well, that's a really simple, straightforward way to visualize data for just a single variable.
Okay, so let's make this stick with an example. Imagine a survey of grade 12 students about part-time jobs. We've got tally marks for each homeroom, and then we've turned that into a frequency. Now, if we want to show this data visually, what's the best way to do it? We're looking at one main thing here, right? The frequency of jobs across different homerooms.
Right. And as these learning materials point out, when you're dealing with one primary variable like that, you want to see how often each category happens.
Like each homeroom.
Yeah, exactly. Dot plots or bar graphs are your go-to. It's because only one of the axes is really representing the variable itself. The other is showing the frequency or the item being measured.
So looking at that homeroom data, you could immediately say...
You could immediately say something like, wow, okay, more students in 12C have part-time jobs than in any other homeroom. That's the kind of, quick insight visualization gives you.
Okay, here's another one. Example 2. We surveyed 15 teenagers, recorded their age, and how many hours of physical activity they do each week. Now we've got two things we're measuring for each person.
Two things, right. Age and activity hours.
So what kind of graph works best here?
Well, since we have two variables, age and physical activity, and we're probably interested in seeing if there's a connection between them.
Yeah, like do older teens exercise more or less?
Exactly. A scatter plot is the way to go. One axis is age, the other is activity hours, and each teenager becomes a single point on that graph.
Right.
And what's cool here is that this setup lets us ask different kinds of questions from the same data.
Like what? Give us a couple of different angles.
Well, a one variable question might be something simple like, what's the range of ages in this group? You just look at the age data for that.
Okay.
But if you wanted to know, is there a general tendency for older teenagers in this group to exercise more or maybe less? That's a two-variable question.
And that's where the scatter plot shines.
That's exactly what the scatter plot, showing both age and activity, is perfect for answering.
All right, let's shift our focus now to how we actually get this data in the first place. Running effective surveys.
Oh, this is so key, isn't it? A good survey isn't just throwing questions out there.
No, absolutely not.
It needs to be really focused on what you want to find out. And it's a partnership, right?
Yeah.
The interviewer and the interviewee.
Absolutely. The interviewer has to do the heavy lifting up front, figuring out exactly what information is needed, crafting questions that are clear, unbiased, and planning the order so the survey flows logically.
Right.
Then, if the interviewee agrees to participate, their responsibility is basically to give honest answers. And these materials we're looking at make a really important point. The interviewer can actually influence how truthful the responses are.
That's right. How you ask, the setting, it all matters.
So let's talk about the different types of questions. We've got open-ended versus closed-ended.
Precisely. Open-ended questions give people space to answer in their own words. You get that rich, sort of qualitative data.
Like, how do you feel about...
Yeah, what are your thoughts on X? Or what changes would you like to see? Things like that. Closed-ended questions, on the other hand, give you a specific set of answer choices. Much easier to quantify.
And within closed-ended, there are different styles too. We have ones asking for specific info, like checking an age range box.
Yep, information question.
Then you've got checklists, like which of these sports do you enjoy? You can tick multiple.
Right, checklists.
Rating scales are interesting. How satisfied are you on a scale of 1 to 5?
Very common. Or like rating the importance of different things, maybe from 0 to 4.
And finally, ranking questions asking you to put things in order, like your restaurant preferences from most to least important.
Exactly. And each of these closed-ended types has its place, depending on what info you need. Now, once you've carefully crafted your survey, there's something really critical to watch out for. Bias.
Ah, bias, the sneaky saboteur of good data. Our sources define it as anything that systematically pushes your results in a certain direction, so you get a skewed picture.
Yeah, it's not random error, it's systematic. And there are several different types.
Okay, like what?
Well, let's start with sampling bias. This happens when the group you survey your sample isn't really a fair reflection of the larger group, the population you're interested in. Usually comes down to how you pick them.
So like only surveying people who walk past a certain street corner.
Exactly. Or that online poll you see, you got to ask, who isn't taking that poll? Who's being left out? That's sampling bias.
Okay, what else?
Then there's non-response bias, or sometimes called voluntary response bias. This is where certain groups just don't participate, so their views are missing.
Or maybe only people with really strong opinions bother to respond.
That's the voluntary response part, yeah. You hear mostly from the extremes.
Hmm.
Another big one is response bias. This is when people do answer, but they give inaccurate information.
Why would they do that?
Oh, lots of reasons. They might want to look good, maybe try to please the researcher, give the socially acceptable answer.
Or maybe they're embarrassed about the real answer.
For sure, fear or embarrassment can definitely play a role.
And the last one mentioned here is measurement bias. Problems with how you collect the data.
Right, like the way you ask the question itself. A classic example is a leading question. The wording kind of nudges people towards a certain answer.
Gotcha. Don't you agree, that sort of thing?
Exactly like that. Okay, so our materials give a really clear example of this bias stuff in action. It's about Rebecca running for student council president. Her campaign manager wants to know how much support she has.
Okay.
Plan A, survey the first 50 students who walk into the cafeteria during one specific lunch period. What problems do you see there?
Well, straight away, one lunch period. Not everyone might be there then, right? So you're missing people.
Definitely. Sampling bias.
And just grabbing the first 50, that feels convenient, but not very random.
That's a convenient sampling. Not great for getting a representative view.
Mm-hmm.
Okay, Plan B tries to improve. They give a questionnaire to one person from each homeroom. Better reach, but still potential issues.
Well, what if that one person chosen just doesn't bother to fill it out? That's non-response bias again, isn't it?
Could be.
And even if they do, just picking one person doesn't mean they represent everyone else in that homeroom.
Good point. It's not necessarily a random sample within the homeroom.
So the challenge is Plan C. What would make a better plan? Minimize these biases.
Well, you'd need some kind of truly random selection process, wouldn't you?
Yeah, maybe randomly pick students from the full school list or randomly from each homeroom list across different times.
Right. And you'd also want to think about how to encourage participation and make sure people feel comfortable giving honest answers.
Less about convenience, more about randomness and representation.
Yeah.
Okay, so that's survey design. Let's move on to the actual nuts and bolts of getting the data, collecting and organizing it.
Right. So when it comes to data, we generally talk about two main types. Primary data is stuff you gather yourself, experiments, observations.
You collect it firsthand.
Exactly. Secondary data is data someone else already collected. Think government stats, previous studies.
So is primary always better?
Often it's ideal because you control the collection. But secondary data can be incredibly useful, especially for large-scale stuff. The key thing is, if you use secondary data, you always need to cite your source. Know where it came from.
Makes sense. And if you are collecting primary data, say through an experiment, how do you keep it accurate and fair?
Precision and fairness are key. The materials highlight some steps. Plan everything meticulously beforehand.
Like your procedures?
Procedures. How you'll record things, have clear recording sheets ready. Use random sampling if you're selecting participants. And crucially, keep the conditions consistent for everyone involved.
So everyone gets the same experience.
As much as possible, yes. The whole process usually goes: design the experiment, get your participants, run it, organize the data you collect, display it, often a scatter plot, if you have two variables.
Like we talked about earlier.
Right. And then, finally, analyze what it all means.
Now, when you're looking at that data, sometimes you see outliers, points that just look way off.
Exactly. Outliers.
Yeah.
Values that are really extreme compared to the general pattern of the rest of your data.
So what do you do with them? Check them out.
Not so fast. These materials suggest you can sometimes remove an outlier, but only if you have a really good reason.
Like there was a typo entering the data.
Yeah, a data entry error, maybe a measurement mistake, or if it's clear that data point isn't actually from the group you're studying, like measuring heights of adults and accidentally including a child's height.
Okay.
But if you can't find a clear error, the advice is generally to keep the outlier, but make a note of it. And definitely consider how it might be affecting your results, like pulling an average way up or down.
Okay. Be cautious about removing them. Now, we mentioned random sampling earlier for surveys, but there are different techniques for sampling in general, right, to make sure it's representative.
That's right. Several methods. Simple random sampling is kind of the ideal. Every single member of the population has an equal chance of being picked, and each pick is independent, like drawing names from a hat.
Okay, the gold standard.
Pretty much. Then there's systematic random sampling. You need an ordered list of your population first. You randomly pick a starting point.
Like the 7th person on the list.
Exactly. And then you pick every nth person after that, like every 10th person or 20th, whatever interval you choose. It's efficient, but that initial list needs to be random itself, or you could introduce bias.
Right, if the list is ordered in some meaningful way.
Precisely. Then we have stratified random sampling. This is smart when your population has distinct subgroups, or strata.
Like different departments in a company or different age groups?
Perfect examples. You divide the population into those strata, and then you take a simple random sample from each stratum, usually making sure the sample size from each group is proportional to its size in the whole population.
So you ensure all groups are represented fairly.
That's the goal. Cluster random sampling is a bit different. You divide the population into groups, or clusters, often based on geography, like different city blocks or schools.
Sure.
Then you randomly select some of those clusters. And here's the key part. You then survey everyone within the selected clusters.
So you pick groups, then sample everyone in those chosen groups.
Right. Can be more practical if the population is spread out. And finally, multi-stage random sampling just combines these methods, like randomly pick regions, then randomly pick towns within those regions, then randomly pick households within those towns.
Layers of random selection.
Exactly. Each method has its pros and cons depending on the situation.
Okay, that's a lot of ways to get a good sample. So we've got our data, hopefully unbiased and well collected. Now, how do we start to see patterns? That brings us to the line of best fit.
Yes, the line of best fit. Remember, a scatter plot helps us visualize the relationship between two variables.
Right, the dots on the graph.
And typically, we put the independent variable, the one we think might be influencing the other, on the horizontal x-axis.
Like age or study hours.
Yeah. And the dependent variable, the one that might be affected, like height or grades, goes on the vertical y-axis.
Okay, so the line of best fit, what is it doing?
It's essentially a straight line drawn through that cloud of points on the scatter plot that tries to summarize the general trend. It aims to get as close as possible to all the points overall.
Like an average line through the data?
Kind of, yeah. A visual summary of the relationship. And looking at that line on the scatter plot tells you a lot.
What kind of things can you tell?
Well, first, the type of correlation. Do the points roughly follow a straight line? That's linear correlation.
Or maybe a curve.
Could be nonlinear. Or maybe there's just no pattern at all, no correlation.
Yeah.
Then the strength. Are the points packed tightly around the line?
That would be strong correlation.
Strong correlation, yes. If they're spread out widely, it's weaker. If it's just a random scatter, there's probably no relationship.
And the direction, up or down.
Direction, too. Is it positive correlation? As one variable goes up, the other tends to go up, the line slopes upwards?
Like height and age in kids?
Usually, yeah. Or is it negative correlation? As one goes up, the other tends to go down. The line slopes downwards.
Maybe like hours spent gaming versus grades for some people.
Could be. And of course, looking at the plot also helps you spot those outliers we mentioned, the points that are way off the general trend.
And there's a number for this, right? The correlation coefficient, R.
Yes, R. It's a specific number between +1 and -1. It gives you a precise measure of the strength and direction of a linear relationship.
Okay, so closer to +1 or -1 means?
Stronger linear correlation. +1 is a perfect positive linear relationship matters if one is a perfect negative linear relationship.
And close to zero.
Close to zero means a very weak linear relationship, or none at all. Basically, RIN tells you how well a straight line fits your data.
But correlation isn't causation.
Absolutely. A crucial point. Just because two things trend together doesn't mean one causes the other.
Yep.
There could be a third factor involved, or it could just be coincidence.
The classic ice cream sales and crime rates example both go up in summer.
But ice cream doesn't cause crime. Heat is the likely third factor influencing both. Always look deeper than just the correlation number.
Okay. These materials also distinguish between correlation, just seeing a relationship exists, and linear regression. What's the difference there?
It's subtle but important. Correlation identifies if there's a relationship and how strong it is. Linear regression goes a step further. It's the process of finding the actual mathematical equation for that line of best fit.
The y equals mx plus b thing.
Exactly. Once you have that equation, you can use it to make predictions. That's where we get into extrapolation.
Predicting beyond your data range.
Right. And interpolation, which is estimating values within the range of your data. The examples in the materials, like height versus arm span or dieting weeks versus mass, show how you'd use that line equation for prediction.
Now, drawing that line by eye is one thing, but technology, that really helps here, right?
Oh, massively.
Yeah.
Graphing software, like Desmos mentioned here, makes this super easy. You plug in your data.
Like the Toronto Marathon times over the years in example 1.
Exactly. You input the years and the times. The software instantly creates the scatter plot, draws the best possible line of fit mathematically, and gives you the equation y equals mx plus b.
And those R values too.
Yep, it'll often give you r, the correlation coefficient, and r squared, which tells you the proportion of variation in the dependent variable explained by the independent one.
Yeah.
Makes it really easy to see the trend, its strength, the slope, identify outliers.
Much more precise than eyeballing it.
Definitely. And example 2 with the Canada-USA exchange rate shows the same thing. It even notes you might need to prep your data slightly first, like calculating number of years from a start date.
But again, technology handles the visualization and the calculation of the line and correlation easily.
For sure. Which brings us to the crucial part. Analyzing the data. What do we actually do with this plot, this line, these numbers?
Well, thinking back to correlation versus causation, we need to consider if there's actually a cause and effect relationship, right?
Yes. That stronger claim. It means a change in the independent variable directly causes a predictable change in the dependent one. Much harder to prove than just correlation.
And we also need to watch out for those influential outliers again, the ones that might be pulling the line.
Absolutely. A single point, if it's far enough out, can dramatically change the slope and intercept of your line of best fit, potentially giving a misleading picture of the overall trend.
So it's important to remember the limits. If our sample was bad or too small,
then our conclusions might be shaky. Outliers, whether they're errors or just rare cases, can mess things up, especially with small samples.
and if that R value, the correlation coefficient, is really low,
Then the line of best fit isn't very meaningful. Trying to extrapolate or predict far beyond your data, using a line with a very weak correlation is risky business. It's probably not reliable.
the material shows some examples of regression problems, right? In example 2 of this section.
Yeah, they highlight common pitfalls, like a scatter plot where you just can't see any trend at all.
Just random dots.
Pretty much. Another shows a really low value, like 0.145, suggesting basically no linear relationship, even if the software draws a line.
So the line doesn't mean much then.
Not really. There's also an example with a clear outlier that's yanking the line of best fit way off from where the rest of the points seem to be heading.
And you need to investigate that outlier. Check for errors.
Exactly. See if it's a mistake before you even think about removing it. And if you keep it, note its influence.
And they even show a regression equation that just makes no sense.
Yeah, like predicting time based on a plant's height. Time is almost always the independent variable. It just shows you need to apply common sense.
So don't just trust the numbers blindly. Look at the graph, check their R value, investigate outliers, ask if it makes sense.
That's the key takeaway. And remember, real-world trends can change. External factors pop up. Data analysis isn't usually a one-shot deal.
right. Okay, we've looked at relationships between variables. Now let's zoom back in on summarizing a single set of data. Measures of central tendency.
Right, trying to find the center or typical value in your data. The big three are mean, median, and mode.
Mean is just the average, add them up, divide by how many.
Yep, median is the middle value when you line them all up in order.
And mode is the one that shows up most often.
Exactly. And they each tell you slightly different things. The mean is sensitive to extreme values, outliers.
So one really high score can pull the average up.
Right. The median isn't affected by outliers nearly as much, so it's often better for skewed data. Mode is useful for categorical data or finding the most common response.
Example 1 here uses exam results for 2 classes to show this. Calculate mean, median, mode for both.
And you can compare. Maybe one class has a higher average mean, but the other has a higher typical score, median, if there are some low scores pulling the mean down.
Okay. Then there's the weighted mean. What's that about?
That's when some data points count more than others. They have different weights.
Like in calculating a course grade, tests are worth more than quizzes.
Perfect example. You multiply each score by its weight, add all those up, and then divide by the sum of the weights, not just the number of scores.
So it reflects the importance of each part.
Exactly. Example 2 shows this with a student's math, marks quizzes, tests, assignments, all weighted differently. The weighted mean gives a truer picture of their overall grade than a simple average. The weights tell you how much each component contributes.
Got it. The materials also bring in quartiles. How do they help?
Quartiles help us understand the spread or dispersion of the data around the median. They divide your ordered data into 4 equal chunks.
4 quarters?
Yep. The first quartile, Q1, is the point below which 25% of the data lies. Q2 is the median 50% below. And Q3 is the point below which 75% lies.
So Q1 is the median of the lower half, and Q3 is the median of the upper half, roughly.
Essentially, yes. And the difference between Q3 and Q1 is called the interquartile range, the IQR.
IQR, what does that tell us?
It tells you the range covered by the middle 50% of your data. It's a good measure of spread that isn't affected by extreme outliers.
Ah, okay. Example 3 shows how to find Q1, Q2, Q3, and the IQR, and mentions box and whisker plots.
Yeah, box plots are a great way to visualize the median, quartiles, and the range of the data, including potential outliers. Technology like Desmos makes creating them easy.
And finally in this part, percentiles.
Percentiles are like quartiles, but they divide the data into 100 equal intervals.
So the 50th percentile is the median.
Exactly. The 25th percentile is a Q1, the 75th is Q3. Percentiles are really useful for ranking an individual score within a larger group.
Like standardized test results, you scored in the 85th percentile.
Precisely. It means you scored better than 85% of the people who took the test. Example 4 with the student heights shows how to find the score at a specific percentile, like the 90th, or find the percentile rank of a specific score, like a height of 166 centimeters.
Okay, useful for comparisons. So we've covered describing single data sets and relationships. Now let's look at using data for broader comparisons, like between countries, using statistical indices.
Right. Indices are powerful for tracking changes and making comparisons, often over time or across different groups. A really basic but vital concept is per capita.
Per person.
Literally, per head or per person. You take a total value for a population like wealth or debt and divide it by the number of people.
Why is that useful?
It allows for fairer comparisons between groups of different sizes. Example 1 calculates Canada's per capita national wealth, then gives you data for other countries, so you can calculate theirs and compare on a more equal footing. A big country might have huge total wealth, but less per person than a smaller, rich country.
Levels the playing field for comparison.
Okay.
Example 2 applies this to national debt.
Yeah, calculating per capita national debt.
Yeah.
It really brings home the scale of debt when you think about it as an amount per individual citizen.
A bit scary sometimes.
Can be. And related to that is net worth in example 3. That's a country's total assets, wealth, minus its total liabilities, debt. Calculating that per capita gives an even better snapshot of overall financial health.
Wealth minus debt per person. Okay.
Then the materials shift to price indices. These help us track how prices change over time.
Inflation and stuff.
Exactly. The big one is the Consumer Price Index, or CPI. Government agencies track this closely. It measures the average change over time in the prices paid by urban consumers for a standard basket of goods and services.
Like food, housing, transportation.
All that stuff. Example 4 shows a CPI graph. It asks you to identify the base year, the year everything else is compared to, usually set to 100.
So a CPI of 110 means prices are 10% higher than the base year.
That's exactly what it means. The example asks you to read the graph, find when costs were lower than the base year, CPI below 100. Find the CPI in a specific year, figure out the change between years, and describe the overall trend. Is inflation happening?
Got it. And the general idea of a statistical index.
It's just a ratio, really. It compares a value at a specific time to a value in a base period, showing the change, often expressed as a percentage change or a factor.
Like the index went up by 5% or it's 1.5 times higher now.
Right. Example 5 looks at the TSX Composite Index that's a major benchmark for the Toronto Stock Exchange. It shows a graph of the index value and trading volume over time.
And asks us to analyze it.
Yeah, calculate the factor of growth or fall between certain dates, find the percentage change over different periods. It shows how these indices are used to track market performance. And it mentions checking out Investopedia for more on CPI and the TSX.
Good resources.
Definitely. So, wow, we've covered a lot in this deep dive, from the absolute basics of variables and graphs.
Yeah, dot plots, scatter plots.
Through designing good surveys, avoiding bias, different sampling methods.
Lines of best fit, correlation, regression.
To summarizing data with mean, median, quartiles, percentiles, and finally these large-scale indices like CPI and per capita measures.
It really is a foundational toolkit for understanding data. And these concepts pop up everywhere, don't they? News reports, business decisions, scientific research.
Absolutely. Being able to navigate and interpret this kind of information is just, well, essential today.
It really is. So maybe a final thought to leave our listeners with.
Yeah. Thinking about everything we've discussed, all the different ways data can be collected, organized, analyzed, maybe even manipulated, what do you, the listener, think are the most critical steps, the absolute must-dos to ensure that the conclusions drawn from data are actually accurate, meaningful, and trustworthy in your own life or work?
That's a great question. What are those non-negotiables for reliable insights? Definitely something to mull over. We hope this deep dive has given you some useful tools and perspectives.
Keep exploring. Keep questioning the data you see.
Thanks for diving deep with us.